I'm going to start by apologizing. This was originally due to be given by my colleague. His name is Antonis Karalis. He couldn't be here. He's better looking than I am, probably much more competent than I am about this. And I'm actually running a chiplet workshop like two rooms down right now. So but what I wanted to do was walk you through the slides he made and give you my intent at them and my interpretation of their intent. And I think the only good news in all of this is I'll probably get you back on schedule. So, okay. So let me go through what his basic thinking. Right. His basic thinking is that if you consider real-time inferencing as a problem definition, real-time inferencing comes with an end-to-end latency constraint. That's sort of the basic problem definition. And what happens is that, so if you want to do real-time inferencing and you think of it as, I've got these multiple stages, you're roughly looking at around a 10 millisecond latency in terms of total time. So I want to give you upfront, don't hold me to these numbers, but I think the intent of the intent of what he's trying is what he's specifying is interesting. So the basic thought process in this is that if you're using a very expensive GPU-based system, fundamentally what you're facing is that in order to use your system resources efficiently, you have to batch your inferencing. And when you batch your inferencing, you encounter a batching latency, which on its own will violate your real-time requirements. So if you're trying to do real-time inferencing, by definition, you'll have to reduce your batch size. And the interesting thing that happens is, once you reduce your batch size, the efficiency with which you use your GPUs goes down dramatically. So the thinking here is, if the efficiency with which you're going to use your GPU goes down dramatically anyway, you can re-architect the system that you're inferencing on. And instead of inferencing, instead of building it with an expensive network infrastructure, what if you could switch over to a commodity network infrastructure? And Nick isn't here when I need him. So the thought process here is, hey, I need to reduce my batch size in order to do real-time inferencing, because batching latency alone can eat up 5 to 6 milliseconds of a decision-making process. So what if I could now switch over to a commodity infrastructure and do a batch size of 1 on a Yosemite? The flip side that you face here is now your packet, if you have a multi-stage neural network where each network is on a different card, each network stage is a different card, your network latency alone can kill you hopping from point A to point B. You switched to cards which are cheaper, and you switch to smaller batch sizes. But as your data is moving from card to card, from network stage to network stage, networking latency alone can hurt you. So so the idea is that if you have in a previous workshop, Nick and a couple of other colleagues from Facebook demonstrated with a metronome NIC, you can actually start controlling your tail latency, and you can budget you can sort of control and manage how much latency you incur. So the thought process is that if you're now switching to a commodity inferencing system and you reduce your batch size to, you're saying trigger an inferencing action on a batch size of 1 or 2, that you need to work on your network latency on a commodity infrastructure, and that you need a NIC which can manage your worst case latency. And this data is from March. So if you go back into March and look at Netronom's presentation at the March 2019 summit, there's some interesting results on how you manage worst case latency using the Netronom NIC. So the basic thinking is that if you're going for a batch size of 1, what you want is then switch to GPUs which or FPGAs or any other inferencing engine whose performance on small batch sizes is the same as that of a much more expensive GPU or a card. But your overall cost of your infrastructure goes down dramatically. That's the working theory of this presentation. And so the idea is that if you can control your latency and if you can control your tail latency, you can use small batch sizes on a commodity infrastructure to do real-time inferencing, right? And that's a basic intent of this presentation. To a first order, I sort of didn't believe it. I'm not sure to a first order, one of the interesting things is that if you look at let me skip past this because I'm still not. So to a first order, there's two classes of NVIDIA GPUs, a T4 and a V100. The very interesting thing is that on a batch size of 1, the performance is on a batch size of 1, they offer comparable performance. And I don't know whether that's a reasonably valid claim or not, in all honesty. I'm hoping somebody else smarter than I am knows this. I apologize for how brief this is, but the basic intent of the talk is if you start reducing if you want to do real-time inferencing, you need to lower your batching latency when you're doing inferencing. And if you're going to lower your batching latency, then you might as well move to a commodity infrastructure. And when you do that, you need to your networking infrastructure, when you have multiple network visits for your inference images, becomes a problem, and you need to control your networking latency. And there's a lot of work that remains to be done, but our basic hunch is, can we get some inferencing workloads up and running on a commodity infrastructure to see what their performance is when you have an end-to-end latency constraint. That's basically it. You can have questions, but I'm not sure I can answer them, but I'm going to give it a shot.
Is there a one-liner on why that particular NIC was going to reduce the latency versus whatever the other thing was making?
Yeah, so there's there is, and except I don't know what the one line is, but it has to do with buffer management. When essentially how you allocate memory buffers to manage your worst case tail latency for the packets. It's I don't remember, but it is. Hang on.
There's some magic there, and then what was the? I think.
Hang on. Maybe I should just. No, don't. That's the part I'm sort of the shakiest on. So
the idea was that the DGX systems were using InfiniBand.
No. So just to be clear, if you look at the performance data, let's say on NVIDIA's website, right? So the V100 and the T4 offer very similar performance for batch sizes of 1. There's something to do with an internal GPU architecture where at low batch sizes.
But, I'm sorry. So
fire away. You can.
My only question was like the assumption. One of the assumptions here was that the networking was the bottleneck.
No, not the bottleneck. I got to be very clear about this. If your batch, so the sort of assumption chain is, if you have batching increases your latency. You need batching to improve the efficiency with which you use an expensive system.
Yeah.
And if you lower, but batching also basically incurs aggregation latency. Batching and inferencing increases aggregation.
I'm okay with
You're okay with all that. So then the thing comes down to, okay, if you go down to a batch size of 1,
Yeah.
you really don't need this expensive infrastructure to move your data around. There's enough data, because if you look at a batch size of 1 and you look at a GPU and you look at the rate at which a GPU processes images, it kind of comes out to like a PCI Gen 3 bandwidth roughly. So it kind of matches to the bandwidth the Yosemite platform offers you. So, hey, you've got enough bandwidth on a commodity platform to feed the GPU with a batch size of 1. But then you run into the problem that the network latency in a commodity platform is unpredictable, not that it's the bottleneck. And if it's unpredictable, then you find it harder to guarantee your real-time latency inferencing constraint.
I guess that was my question then. So it's just the commodity NIC infrastructure is unpredictable latency versus the DGX with InfiniBand was predictable latency, isn't that?
The DGX with InfiniBand is over-provisioned to feed the beast, as it were. Right? The commodity NIC with a batch size of 1. A Yosemite server in general, you have variable latency. You need to bound your tail latency. And if you want to do real-time inferencing, you need to bound your tail latency. That's the basic thinking. And about 6 months ago, Netronome did a bunch of demonstrations on if you use a Netronome NIC, you can bound the worst case latency. So if you bound the worst case latency, you're in a greater position, more likely to be able to make real-time inferencing guarantees. That's a chain of reasoning, as it were.
Thanks.
Yes, fire away.
Well, so I think along the same line, all that you were saying, go to commodity infrastructure, independent from the given implementation. You're saying your network latency matters. If you can bound it, then you can really use this commodity.
Exactly. That's right. That's right. So the moment you stop batching, your bandwidth requirements for each GPU go down. The moment your bandwidth requirements for each GPU go down, you can move to a commodity infrastructure. But then you run into, hey, if I want to do real-time inferencing, I need to bound my network latency, or I need to bound my system latency, which the network is one component, and I need to bound that in some fashion. That's the basic thinking. Fair enough, and I will get you an answer. But it is essentially bounding worst case tail latency. Okay, I apologize. Thank you.
Thank you.